The problem of trisecting an angle can be done using a device called conchoid of Nicomedes. How do you create a conchoid? Here you have a fixed line, we call this fixed line CD, and a fixed point. There's a fixed point on the device, but this fixed point should not be on the line, so therefore we pick a O, which is fixed point, and a fixed distance H, and draw a line OB and intersecting CD at E. So OB, draw a line intersecting this line CD at the point E, and this H is used to determine, so from here to here, this is H, and you keep track of this point X. So at different location, like when this is here, you make sure that this is H. So then this is the point on the conchoid. So the conchoid, that's how we determine those points on the conchoid. And there's actually, if you look at the other side, EY to be the other side, that's another point on the other side. But we do not need that for trisecting an angle, but that's the lower branch of a conchoid. Now, the locus of X is a branch of conchoid. When we say locus, that means the collection of points. Here, we want to show that this device can actually trisect an angle by showing this. So if you give me an angle, say AOB. So in this case, AOB is the angle given. And if EO is half of XE, so in other words, this distance EO is half of this distance XE, then this angle AOB is trisected by this segment GO, where this G is a point, is the intersection of this segment EG, which is a segment perpendicular to CD, and the OG. Where this G is the segment, is the intersection of the conchoid, and this EG, where EG is perpendicular to ED. So basically what it means is this angle is a third of this angle. That's what we claim. So how do we prove that? This is how we prove that. So now, what is given? The given information is XE is twice of the EO, or EO is half of XE. So in other words, this is twice of that. And let's label, let me erase that. So this figure is a magnified portion of this figure here. Okay, let's label this intersection as I, which is this guy. So we also given GI equals XE. I do not need the bar when I denote length. This is because the conchoid, you remember the conchoid, it's fixed distance from the line to the curve, right? So they're both edge. So we do know that to be on a conchoid, these two segments should be equal. GI is equal to XE. And what do we want to prove? We want to prove angle AOB is equal to 3 times of the angle AOG. Okay. So that means, in other words, angle EOG, which is this guy, should be twice of this smallest angle, which is this guy, is twice of the angle FOG. And this figure is just a magnified figure of this part. Okay, so let's work on this one. This one is a little easier to work on. So again, we want to show that this angle is twice of this angle. That's what we want to show. So first of all, let's let H be a point which is the midpoint of this GI. So right there, this is the H, which is the midpoint of this GI. Let H be midpoint of segment GI. Because it's midpoint, then we can certainly conclude that GH so GH equals HI, right? And equals EH. I hope that you are still fresh, that because this is 90-degree angle, and if this is midpoint, EH should be equal to GH equals HI. This is one of the homework problem. And also equals EO. And why this is equal to EO? If you remember, we claimed that earlier. We know EO is half of the XE. And this XE is the same as GI. They are the same distance. So therefore, EO is half of the GI, which is, and then GH is half of the GI. So therefore, they're equal. And because of that, I now can claim, so therefore, angle EOH is equal to angle EHO. That means is equal to EHO because these two lengths are equal. This is an isosceles triangle. So therefore, these two angles are equal, right? Now, this angle being the external angle of this triangle GHE. So therefore, this angle is actually equal to the angle of this sum of these two internal angles. So again, this angle is equal to sum of this and this. This is actually a fact from number 6 in appendix 5. So I'm going to write this down. So EHO is actually equal to sum of the angle HGE plus this angle HEG. And this is by number 6 in appendix 5. Okay. And now one more thing to note is we already mentioned that GH is equal to HE. Therefore, this actually is an isosceles triangle, and therefore these two angles are equal. And therefore, I'm gonna use that these two are equal, therefore it's equal to twice of the angle HGE. Now, I think we're almost ready. Now, OF, this is the OF. OF is a line perpendicular to CD. and EG is also perpendicular line to CD. Therefore, these two lines are parallel. This is a known fact from the construction. So therefore the alternative angle should be equal, which means this angle FOI should be equal to this angle, which is HGE. So let's write this down, because FO is actually parallel to EG. And why is that? That's coming from here, okay? This FO is the same as OA. So therefore, the angles are equal. The angle FOI is congruent to angle HGE. Now, we are done. Now, I would like you to begin with this angle angle EOH is equal to, here, this is the endpoint. So you know this is congruent, right? So EOH is equal to twice of the HGE. And what is HGE? HGE is congruent to FOI. So twice of the angle FOI. Okay. So I think that's what we want to prove. I want you to look at, we want to prove EOG. EOG is the same as EOH. EOG is the same as EOH, which is this angle. And FOG, which is FOG, is the same as angle FOI. So that's what we want to prove. Exactly. So that's the end of the proof. And so that proves when we use a conchoid, we actually can trisect an angle AOB. And how do we do that? Again, this is how we do that. We place this angle so that the vertex overlaps with O. And then we make sure that the length of this is twice of this. Now the question is, what if it is not, right? If it is not, then make it happen. How do you make it happen? You can adjust the vertex. You can adjust the move the position of this, like find a conchoid so that EX is twice of the OE. That's what we show in class. And once you make sure that this angle coincides with this conchoid with vertex O, and then once you make sure that OE is twice of XE, then construct a perpendicular line through this point E to find this intersection, the intersection of the vertical line and the conchoid, and OG will trisect this angle.